Hello guys, welcome to today's episode of Calculus of Variation. So today I'll be proving the fundamental lemma of calculus of variation. So the first thing I'll ask you is, what do you understand by lemma? So anytime you hear lemma is just, I'll try to be free so everyone understand what I'm saying. Like I'll use the least explanation to explain so everyone understand. So lemma is just like a proven statement used to prove another statement. Like I have a statement like this and I want to prove this statement. After proving this statement, then I'll use it for another statement. Then I can call this statement a lemma. You can also say it is a minor. Okay, I'm not give it that one. Let me just take it that way. It's a statement that you can use to prove another statement. So when you have this calculus of variation, the statement of calculus of variation, it is very important in proving Eulers Langrange equation. Like if you don't know this and then you are proving Eulers Langrange equation, then there might be a little bit problem in between. So the statement states, or it goes thus: if for every continuous function eta of x, and you have the integral from x1 to x2, phi of x, eta of x dx equals 0, where your phi of x is a continuous function on the interval x1, x2. What we want to prove is that phi of x is equal to 0 on this same interval. Now what I'm saying is, let me illustrate that for you so you understand. What I am saying is, suppose I have integral from x1 to x2. Suppose I have this integral from x1 to x2, 2x phi of eta of x dx equals 0. What we're saying is, this lemma is telling us that whatever I have here, which is my 2x, it must be equal to what? 0. I'm only giving this as an illustration. So what we're trying to say here, that if you have this integral, then phi of x must be equal to what? 0. That means if I have something like this, anything I have here will be equal to what? 0. So I'll explain this now vividly. So the first thing is that we'll be proving using contradiction. Contradiction, that means we are asked to prove that phi of x equals 0, right? Then we'll prove that, okay, what if I have my phi of x not equal to 0? That means if I am able to prove this, then this is not true. But if I am unable to prove this, let's say I want to use this contradiction, right, that phi of x is not equal to 0. So if this is not true, if phi of x is equal to 0, then this integral is correct, right? But then if I'm using phi of x not equal to 0, then I end up having this I'm not having this integral. Then I will say that this contradiction is wrong. Then phi of x equals 0. Let me explain this again. We are going to prove using contradiction. That implies what we want to prove is that phi of x equals 0, right? But then we're proving that phi of x is not equal to 0. So if this is not true, we're supposed to prove that this is true, right? So if this is not true, that means phi of x equals 0 is what? True. So this is what I'm trying to say. So we're proving using contradiction. Now, the first thing you are going to do, you don't have to memorize anything. If you are looking at the statement, you have interval x1 and x2, right? So I'll tell myself that let us pick a point inside this interval. So let us pick, correct it anyway, pick a point x equals x bar. That is, let's say that is, I have this, I have my y-axis and I have my x-axis. So if I have y-axis and I have my x-axis, on this interval, we have the interval is what? x1, x2, right? So let's say I have x1 here and I have x2 here. So if we're picking a point x equals x bar, that means now you said, this is a closed interval, right? So this interval is closed. So I'm picking a point x equals x bar. So let's say I have x1 bar here and I have x2 bar here. So let us pick this point. Now if we're picking this point, then you don't, like I said, you don't have to cram anything, right? Go back to your integral. What is the first thing you are seeing here? If you look at the integral, you're seeing what x1 and x2. I worked on that already. The next thing I have to work on is my what? File of what? X. So I'll now tell myself that, okay, my file of x from the statement, what is it? File of x is a what? Continuous what? Function. So I'll now say we want to prove that file of x is not equal to what? 0. This is what we want to prove, right? So we're going to be proving by what? Contradiction. Prove by contradiction. So if I am proving by contradiction, it implies that I'm going to do opposite of this. I've already explained that, right? So now we want to prove that file of x is not equal to 0. Then I'll now go back to my statement. What my statement is saying? My statement is saying that what? My file of x is a what? Continuous function. Then I'll now say, since my file of x is a what? Continuous. You can say since, or you say suppose, or you let your file of x be continuous function. So since file of x is a continuous function, anything that is continuous, what does it mean? That means that thing is what? Differentiable. It means at every point it has a what? Derivative, isn't it? So that means that thing can never be equal to 0. So I'll now say it implies that my file of x is not equal to what? 0, since it is continuous. Now inside these points, x1 bar and x2 bar, I want to maintain a sign. So I'll tell myself that, okay, since file of x is a continuous function and file of x is not equal to 0, then I'll not tell myself that then file of x maintains a sign in this neighborhood, inside this neighborhood, x1 prime bar and x2 bar. So I'll tell myself that, then file of x maintains a sign, or it maintains its sign, anyone. So right now I'm working with positive sign. I'll still explain this, can take negative or positive, but I want to explain using positive first to you. So then file of x maintains a positive sign in a certain neighborhood. That means people that are beside it, right? People that are living around it. So in this certain neighborhood, x1 bar and x2 bar. So that means in a closed interval, x1 bar and x2 bar, which is the same thing as x1 bar less than or equal to x less than or equal to what? X2 bar. It's the same thing. So the first thing, like I said, you come to this place, right? And then you say, if I have this by contradiction, I want to prove this by contradiction. Then in the statement, file of x is a continuous function, and anything that is continuous, it implies that my file of x is not equal to what? 0. Then I'll not say, then my file of x maintains a sign. I said I want to treat positive sign first. It will maintain either sign. I'll explain to you how and why. So in a certain neighborhood, this. So if I have this, I'm done with file of x, and I want to go to the next man here. What is the next man here? Is what? Eta of what? X. I'll now say, since eta of x is an arbitrary function, like we said here, eta of x is a what? Continuous what? Function. So I say, since eta of x is an arbitrary function, we may also choose, then I can also choose is what? Maintain a sign inside this. You know, this one is continuous, right? So if eta of x is also continuous, so I'll now say, since eta of x is also is an arbitrary function, anyhow, is, let me use this, an arbitrary function, it implies that what? It implies that I can also choose, we may also, see, you can just, when you are proving, as far as you know what you are doing, you can write it the way you like. So we may also choose what? Eta of x to maintain the sign, the same sign that is inside this interval, which is x1 bar, the same sign in this interval, x1 bar comma x2 bar. So if I'm choosing this, if I want eta of x to be this, then it implies that any look, I said eta of x is an arbitrary function, so we also choose eta of x to maintain the sign inside this boundary. That means anything outside this boundary, outside this x1 bar and x2 bar, anything that's outside the boundary, then I can say it's what vanish, or it will turn to what 0. Then I'll not tell you that it implies that my eta of x will be equal to 0 if it is outside what the boundary, outside the what boundary, x1 bar comma what x2 bar. So if it is outside this boundary, it will what vanish. It will what the same thing as what it is going to vanish. So if I have this now, I'll now recall, I'm done with all this. I said the first thing you do is to touch this, and also touch this, right? So I'm done with this. Then I'll now recall that under property of definite integral, I have that if I have this integral from x1 to x2, phi of x, eta of x dx is going to be equal to, if you're working with property of definite integral, it implies that I'll integrate this like this, starting from x1 to x1 bar, then from x1 bar to x2 bar, then from x2 bar towards x2. So that's what I'm going to do. So this is going to be equal to, first one is from x1 towards x1 bar, so it's going to be integral from x1 to x1 bar, phi of x, eta of x dx, plus, then I'm moving right from this x1 towards x2 bar, integral from x1 bar to x2 bar, phi of x, eta of x dx, then plus integral from what x2 bar to, because we stopped at x2 bar, right? So x2 bar towards x2, so x2 bar to x2, phi of x, eta of x dx. Now, like we said initially, we said anytime this eta of x, he said eta of x is an arbitrary function, we may also choose eta of x to maintain the sign. And what sign did we choose for this one? Positive, right? So if this is also positive, for instance, so if this is also positive, for instance, it implies that, and I said eta of x equals 0, or it will vanish when it is outside this was boundary. That means if we have x1 and x1 bar, if the boundary is x1 and x1 bar, this will turn towards 0. If the boundary is x2 bar and x2, because it's outside x1 bar and x2 bar, then it's turned towards 0. That means automatically here I can have, it implies that my integral from x1 to x2, phi of x, eta of x dx equals 0 plus this here won't turn to 0. Why? Because we said what? It will take a sign when it is inside this what? Neighbor, when it's inside this interval. So I'll now have integral from x1 bar to x2 bar, phi of x, eta of x dx plus what? 0. And we said this eta of x here is going to be what? Positive. So that means if eta of x is positive here positive, right? Here is also what? Positive. When you have plus times plus, will give you what? Positive. Let's say I take eta of x, like I said you can take any sign, right? So let's say I take it, phi of x to be negative, eta of x will also be negative, because I said we may also choose eta of x to maintain the same sign inside the interval. So that means some what? Negative. So minus times minus will give you what? Positive. So that implies that if both are the same sign, then it means they will always be what? Positive. And when you say something is positive, it means that it is greater than what? 0. Anytime you say something is positive, it implies that that thing is greater than what? 0. Then I'll not tell you that it implies that my integral from x1 to x2, phi of x, eta of x dx is what? Positive. Now, if it is positive, it also implies that integral from x1 to x2, phi of x, eta of x dx greater than what? 0. But by definition, what's our definition from the beginning? We said this is equal to what? 0, right? And I told you already from the beginning that if we prove by contradiction and we're not getting this, it means that when our file equals to 0, not equals to 0, it means that this is what's not correct. Like I said in the beginning, if you remember, I said if we are proving contradiction and we don't end up having this equal to 0, it implies that what this is not what true. So you come here and say, but by definition, integral from x1 to x2 phi of x eta of x dx is equal to 0. That means they are contradicting, right? That means this phi of x not equal to 0 is not true. Then it implies that since this is not true, since phi of x not equal to 0 is not correct, then it implies phi of x equal to 0 is what correct, or it is what true, which proves the fundamental lemma that we want to prove. That means phi of x equals to 0 inside what the same interval. So I hope you understand. That's why if we are solving trying to prove the Eulers Langrange equation of the first form, notice that you are going to have something of this format. Let me write something out so you see. I get what I'm saying now. So you won't just cram, you understand every aspect of what you are doing. So when you are proving the first form of Eulers Langrange equation, which I have explained, so in case you've not probably subscribed to my channel, please, you should do that, and then turn on the notification bell, because I'll be uploading more videos, more explanatory videos for you to understand a lot. So I've explained few videos, I've uploaded few videos on calculus of variation, which is Eulers Langrange. So now for this first Eulers Langrange equation, we have that at a point you'll be having that your integral from x1 to x2 die f die y minus d dx of die f die y prime, like when you are proving, which I have done that before. So you just need to subscribe, and if you really understand this, do like the video, and if you have any question you can comment. I'll ensure that I reply. So you have phi of x dx equals 0. So when you are proving the first form of Eulers Langrange equation, you have this equation at some point. Now look at it, compare this equation here to this equation. Like I told you before, that when you have anything eta of x equals 0, using the fundamental lemma of calculus of variation, we said whatever is beside your eta of x is going to be equal to what? 0. So that means automatically from here this is equal to what? 0, that which is our first Euler Lagrange what equation, that if anytime you have die f die y minus d dx of die f die y prime, say it is equal to what? 0. So this is how we got this, is because we already understand an aspect which is called the fundamental lemma of calculus of variation. So like I said, it is an important lemma in the topic calculus of variation. So if you really do understand what I explained, do like my videos, and if you are new to all these videos, do subscribe. Thank you so much, and you all have a nice day.